on to the final session. As Peter said before, we are one talk down. This session is the second talk from David Chisnell, won't be happening, and we'll move on, but we can be a bit more relaxed with the time. Which is nice if you're the session chair. And so our first talk is about porting Rust, and it's given by Martin Batty.
Hello, everyone. I'm on. Hello. So I'm going to talk about a little bit of implementation work, which is not what we usually have done in the past, that we're doing at work at Kent. We ported Rust to Morello, and we got quite far by this point. So everybody knows the shape of pointers in Morello, but I'll just reiterate it. You know, you've got your lower 64 bits and your upper 64 bits and your validity bit. And performing this porting is essentially a task of understanding how we're going to recognize this change in the pointer size in Rust. So we have a Morello prototype, and we've been using it to test the compiler, get performance numbers, and so on. Those of you who have one of these machines will recognize those stats. There's the machine in its little gamer case. It's nice to have toys, because I'm a theoretician, and we don't have too many, actually. So thank you. I do like this stuff. So yeah, everyone will know this, but Rust has similar aims to Morello in that it wants to provide memory safety. It has a type checker that provides the majority of the guarantee, the type system guarantee. But when part of that guarantee is provided by runtime checks in Rust as well. So there's just a little bit of overhead in Rust in order to provide the memory safety guarantees. But it's all done in software rather than in hardware. So that's why they're one of the reasons I say mostly that it statically verifies memory safety. So we know what safety is. On a machine that is not Morello, this pair of examples, I'll show you in a second, is the flavor of the behavior you're going to get on Rust. So here we're defining an array that's 8 long, but we're accessing outside of that array. So if we run this, try to compile it in Rust, we're going to get an error that recognizes our attempt to violate the bounds of the array. So that's static. The thing is that we can, this is designed to be a systems language, so we have unsafe keyword, which allows us to violate the memory safety guarantees of the language in order to basically perform necessary tasks in building systems code. So if I go ahead and do a similar piece of code here where I access outside the bounds of that array, but I declare that to be unsafe, I'll no longer get caught up by the compiler. I'll be able to build it, and then when I run, I get a segmentation fault because, in fact, I did a bad thing. Okay, so why would we port Rust to Morello? Because the guarantees that the two provide are sort of similar looking. But we think there's lots of interesting opportunities. Not all of them have been sort of realized by this work yet, but you can imagine that the Rust programmer need not worry about many of the violations that may occur on a Morello system, because those are caught by the type checker. Or you might imagine using the hybrid mode to share the responsibility of memory safety guarantees between the software, the compiler, the runtime check, and the hardware for when that's not so easy. And Rust also provides guarantees in the compiler for large parts of the code. So that type system guarantee may be useful in reasoning. So we think these two should actually really belong together. We like the idea of combining these. There's also some interesting questions about the comparison of the semantics between the two. Because here in Morello, our memory safety guarantees are slightly different to those in Rust. It would be good to understand that. The Morello ones have a bounds information that it has like a floating point style representation. It's not precise, whereas Rust's is precise in the type system. So there's some cool semantic comparisons to be done as well, which we haven't got to yet. So what does the actual work of porting this look like? Really fortunately for us, the structure of the Rust compiler looks like this. And you'll see, once I get down here, I can reuse some of the infrastructure built in the Morello project. So I can swap out that the LLVM piece on the end for the Cherry-enabled LLVM piece. And so the main concern is this sort of interface between the front end and the LLVM backend. So this is predominantly a plumbing task, and the backend stuff is mostly sorted by other people in the Morello project. So what we had to do is look at that front piece. And yeah, everything that we needed to change comes down to this change in the pointer size, obviously. So at the very beginning of the project, there was a choice, which is when we say usize in the language, what number are we going to return for that? So on the Morello machine, the storage size of a pointer, of a capability, is 128 bits, but the amount it can address is 64 bits. So you have to basically choose between these two values. There was previous work by Nicholas Sim where he chose usize to be 128 bits, and that seemed to not work as well. We came to the conclusion we would try 64 bits, and that seems to have worked quite well. This does mean that we're doing something which is slightly obnoxious in the specification of the language, because we're blowing apart an implicit equality between the storage size and the addressing size of pointers. And we've been talking to the Rust community to try to, well, to ask them if they would recognize that. But it's complicated, and they haven't agreed to that yet. And talking to Ralph, it seems like it might not be. We'll see. So we've got a little bit of detail on the object layout in the compiler here. Things to note, there's a new pointer width here, which is splitting apart the addressing and storage size of that pointer. We had to do twiddle a couple of knobs here. So atomic pointers via integers we turned off, which is like a little extra guardrail on how provenance is permitted in your Rust code. This restricts going between pointers and integers a bit. And then we had to turn off one of the optimizations here, so the merge functions optimization. And I think we don't have like a really concrete analysis of why that optimization caused things to fail, but we figured out that it was causing us problems, so we turned it off. So otherwise, this is pretty much a standard Rust compiler. Other things we had to do, which I think are interesting, is the Rust compiler has some constant evaluation. And if you think the constant evaluator is going to have pointers in it, it actually does a bit of work with pointers. And that means we needed to make it aware that the size of pointers have changed. But we don't want it like inspecting or manipulating metadata associated with Morello capabilities, because that can invalidate them. So we had to sort of make a bit of space whenever we had a pointer, but make sure that it wasn't accessing metadata in the constant evaluator. Cool, and we certainly don't initialize that data in there. Let's see, what else did we have to do? Right, so there are assumptions all over the compiler, all over the core libraries, and all over the standard libraries about the equality of pointer storage size and addressing size. And the rest of this task was more or less walking those, figuring out whether this could just be cheaply removed or whether there was some deeper problem. And for the most part, they were fairly cheap. So this is a typical little bit of code which is doing some casting from pointers to integers and out again. And this kind of thing just isn't acceptable in Morello. It will cause faults, so we have to find another way to do it. The standard library, as I say, was absolutely similar. So we had to walk that and filter out these issues. It took quite a while because it's big, and it wasn't necessarily very interesting each step of this, but it's it's something that we need to do to build this thing. So we now have the core library, so the compiler, the core library, the standard library building. We have their test suites running and succeeding. And yeah, we've gotten quite far, actually. So this, having this whole, this Rust compiler we can actually use, allows us to go and test the performance with it. This is slightly unfair, as you all know, because this is a piece of prototype hardware. So all of the details of its performance are kind of, they're indicative, but not, well, I suppose it's an upper bound. So there's a particular point of comparison here that's interesting, which is that Rust, the type system, guarantees safety as much as it can, but it has to punt to runtime checks occasionally. And so we can compare software checking with hardware checking. It's not exactly the same thing because of that imprecise bounds information in Morello, and because Morello gives you complete memory safety across everything, and unsafe code isn't covered by the guarantees of Rust. But it's still interesting to look at the difference. So we picked a bunch of crates from crates.io. We got 872 benchmarks. That's 108,000 lines of Rust with 100,000 unsafe lines. And we benchmarked these. We sort of figured out how long they took to run. And we did that over this little sort of 4 quadrants of in this little table. So we've got pure cap, which means Morello's checks are on. We've got hybrid, which means Morello's checks are off. All of this is on the prototype machine, by the way. And then we've got Rust, so just Rust with its checks turned on. And then we've got Rust with its checks turned off. So it's runtime checks. The cost implied by those is removed in that version of Rust. So we've disabled bounds checking. Yeah, we ran all these things. We got time per iteration, and we did a little bit of arithmetic to make that meaningful across the tests. Interesting to note is there wasn't much variance in the times. So I can just show you some graphs without bars on them. And because everything was more or less within a 1% difference of its timing, that's meaningful. Here are the sort of performance numbers we got. So this says 1.5. So we saw quite a high cost for, let's see, pure cap bounds checking. Pure cap no bounds is this crosshatched set of bars. So those are that's implicitly, I guess, the cost of doing the cherry checks on Morello. And the finer crosshatch is hybrid without bounds. So that's running it just with no checks. So there's on average about 39% at the moment cost to this. But as I say, that number is kind of meaningless because this hasn't been optimized, and some concessions have had to be made to get the thing out the door. This is before the benchmark ABI. So we have a to-do, basically, to run that benchmark ABI, and I'm looking forward to seeing what those numbers are. It'll be really interesting. Well, we'll ask you when it's done.
So our experience with benchmark ABIs, for some benchmarks, it makes a huge difference. It eliminates almost all overhead, and for others, it doesn't. And usually it comes down to pointer density and then function call density relative to the overall instruction stream. But I mean, the general thing we're saying right now is if you're not benchmarking with the ABI, benchmark ABI, your performance results are not really meaningful. I mean, obviously they're real, like you measured them, but they may not be indicative or useful in any way. If you need any help, do let us know. We would love to get these same things redone with benchmark ABI because we might discover there are other things that we should be doing something about, and we can then help with that.
So I'm desperate to do that, and it'll be really interesting because our benchmarking suite's big enough to give like some picture of where there might still be points of it being slow and stuff. It'd be cool. Okay, cool. So yes, so we measured overall a slowdown, but yeah, caveats of course due to the benchmarking ABI. And we have a paper, which you can go and inspect to see all the details if you want of that. So like I said before, we tried to sort of sell a change to the Rust community to say, there will be architectures like this, and perhaps we should change the definitions of implicit sizes of things to recognize the difference between storage and addressing size of pointers. And we got a little bit of way discussing with them, and that stalled out, and they weren't very happy with the idea. We're not happy enough to sort of go ahead with it, and we thought, how do we build some additional evidence that this change would be acceptable over the broader code base of Rust? We're changing types here, effectively, and that you'd expect that to break things. But there's all sorts of things that mean these are not common. The idioms where you're translating to and from integers are not common in the code base. We can measure that, it turns out, a little bit, Not every part of it, but some of it we can measure. So that's what we did. So we requested a crater run, which is a run over a massive number of rust crates. So our crater run covers 387,225 projects. What you can do with this is you can't just run anything. You can run a lint, which is going to spot particular shapes of code, basically. So we had found some strict provenance lints, which identified various pieces of code that we believe match up with the problems that that we need to fix if we were to roll this out over the Rust code base. And we get back from that basically a massive log of the errors when you search for these little code snippets. And it gives us an indication of the occurrence in projects of things that might fail if we went and made this compiler, a legitimate Rust compiler. And what we found was less than 1% of projects failed this lint. So right off the bat, there's a very small amount of projects where we encounter problems. And if you think the number of lines in each project where you need to go and change stuff is is only a few in each. So the percentage of lines of code that we might need to edit to fix this casting in and out of pointers is actually integers and pointers is quite small. There's limitations here. So I was talking with Ralph, and he was pointing out that if you use the size of pointers to move up a struct or something, that's going to be a relatively common idiom, and this isn't going to catch that. And we'll have a think about whether we can catch that, but our initial thought is that's quite hard to catch with this process. Our crater run is subject to false negatives and false positives, so it's not perfect even in the bits that it can detect. But it gives you a sort of a broad indication. It's interesting to note that 38% of projects just didn't build. I think this is kind of a fairly wild set of crates, so it's very broad what this lint is covering. We have the script public here. This is the end of the talk, but I want to advertise what we've got here. So we've got a port of Rust to Morello, which is, it's fairly mature, and we think it can be used. We've got binaries for Mac and Linux, which are at this website if you want to shoot the QR code. And yeah, we've measured how much change would be needed to make this a kind of a compiler that can run over the entire code base, and it looks like pretty reasonable, actually. This project forms a basis for us to do further work. So some of that further work is implementing the necessary bits to run this bare metal. So Mike Vollmer is going to be working on that, or he is working on that. We need to update the benchmark targets. And there's other targets like RISC-V that we are thinking about trying to make sure that we support as well. Because I think the first hardware that will actually be commercially available for this, as I understand it, might be available now, is RISC-V based. So that's it. Any questions?
Thank you for an interesting talk. I was just wondering, for the problematic bits of code where you saw things that you couldn't compile, was that generally in unsafe Rust or in safe Rust?
Unsafe Rust.
Yeah. And so could that be just a sign that actually there's code that's potentially buggy or got other problems, or do you think it's something else?
So I tuned in for some of the things, but really I should say actually Sarah Harris has been driving most of this. So she deserves almost all the credit. But the bits that we saw, I don't think so. Most of them didn't seem like bugs that we should be reporting on. I don't think we reported anything from them. But and most of them were easy to fix, if you see what I mean. So they were kind of like idiomatic choices that had been made solely in unsafe code that just didn't match.
It'd be kind of interesting if it's useful as a linter for unsafe Rust.
Oh yeah, okay, yeah. But that lint, to be clear, that lint is not running the compiler, our compiler. It's just looking for code shapes. Yeah.
Have you upstreamed any of changes to the Rust compiler? Not cherry specific, but maybe like just general.
No, we did find a bug in. I'm not going to say because I can't remember exactly. We found a bug in some command line tools before, as we were doing this. So, kind of, I would say like the process of pushing stuff into Morello seems to highlight bugs because things that would fly by the benchmark suite when you're not looking at these things will actually throw cherry exceptions, and so it does form like a different kind of observation.
This is very cool, thanks. I was wondering about the thing you mentioned for the compile time evaluation. So the compile time evaluation engine already prevents actually getting to the bytes of a pointer. Because even without this permission stuff, we don't know where the pointer will be at runtime. So we can't have access to these individual bytes. So I wonder, I don't know how much looked into that, but it seems to me that would be completely sufficient to also handle the opaque permission bytes from the Morello side. I don't know if there's any weird things that happen for the LVM I need to generate, but I would expect you can just make it a big pointer and not make it uninitialized because it will already be opaque.
Oh, that's interesting.
Happy to talk more later if you want.
I think that goes to a level of expertise that I might need Sarah in the room for if you see what I mean. Yeah.
Thank you for this. I agree with you that usize in Rust is a bit of a cock-up. But if you change the semantics of it, then as in change the relationship between the things, now I can't express some programs which I have regrettably written. Are you going to give me a new type as recompense? So, because I can't just I can't change my programs without an equivalent of the old usize.
Yeah, I think we're imagining having two types for the two different things.
And what would the relationship between them be?
Almost always they would be the same, unless you're using Morello. And then they would be different.
So again, I'm interested in this usize thing of people's resistance to pushing on this. I wonder if there's also an issue around alignment, or maybe this turned up when Haruna's thing. That's gradually become clear in C. You need to be able to say a line off to a particular number or to a particular type. Is that visible yet in Rust, or would it just go along with the size?
Know what alignment concerns will throw up for us. This is, if we had Sarah, then she might help. I don't have the but it's interesting enough.
Also, you mentioned you have the port for cross-compilation. What's the story of running, or maybe this is the bare metal, running on the Morello boxes, running the compiler as well, the self-hosting?
Self-hosting. We haven't attempted to do that yet. We just haven't attempted that.
Is your compiler one of the things you put through the linter to see if it worked?
Oh no, I don't know the answer, but that would be embarrassing if it screwed up, wouldn't it? I don't know what the coverage of those crates are. None of our code's in crates.io, I don't believe. So I think it wouldn't be picked up. But I'll go do it and feel shame if it fires.
So I'm curious if the Cherry Rust compiler offers any other opportunities for investigating how to treat certain language features like closures, for example. Can you comment on how you treat closures in Rust, in Cherry Rust? Do you encapsulate them somehow, for example?
Not really. I don't know the answer, but there's a bunch of. This is a different answer. Maybe it helps. I don't know. There's a bunch of Cherry-specific functionality that we could now bring out at the level of Rust, if that makes sense. And we have thought about various bits of that, but we haven't done any of it yet. So you can picture passing through, being able to do Cherry-specific pointer capability manipulation as is provided in the C, but we just haven't done it. So I don't know the answer to your question. Maybe those things would be necessary to support that.
Yeah. Thank you. Just to reply to Ian's questions. So the first one was about alignment and usize. I think my understanding from half following these discussions is that the idea of using usize for provenance, I think, is less contentious. That's easier to catch statically with linters. It won't be perfect, but I think people believe that's kind of okay. I think the bigger problem is the language currently explicitly says that usize is the correct type to use to hold a pointer, which is unfortunate. And that as a result, it is correct for us today to do calculations for sizes of buffers based on using size of usize. And that is something that you cannot check easily with the linter unless you do some very heavyweight static analysis to try and figure out what on earth the arithmetic expression you're using is corresponding to. And I think the concern is that if you change it now, that all that code out there just silently does the wrong thing now, and that you have to catch it at runtime.
I guess the question is how much of that code there is. Do you think that's all over the place?
I have no idea. I think that is really the million-dollar question of just, like, is this a few projects, in which case I guess you just suck it up and catch them as you find them. If it's pervasive, then that's more concerning. But I think intuitively it shouldn't be that much stuff that does this kind of thing, I hope, in Rust. But the second question about self-hosting, LLVM itself can't be built as a pure capability yet. We've had attempts to do that in the past and got most of the way, but there are some sticking points. Doing it as a hybrid binary self-hosting should be totally fine and uninteresting, except for dealing with quirks with paths and things. And on top of that, I had a question actually for Mark. In the past, I think you had your own fork of Morello LLVM that was a bit outdated and had some patches. Do you still have that fork, and do you still need patches, or has the need for that gone away / fixes have been upstreamed or
I
done?
think that in order to try the benchmarking ABI, then we will have to update to a more recent version. So I think we're still in the version.
Okay.
But we want to move. Last time we moved because we did that once. It wasn't that bad.
Okay, we could maybe have one quick question while I switch slides, if anyone has anything. If not, let's start Mark again.